Right. Hi, everyone. Thank you for staying. We're going to start the second part of the workshop. So we will start with a second invited talk. That is a paper that was published in the main conference. And we invited this work in the workshop because we think it's quite complementary to the first keynote talk we had earlier from Dr. Medeiros. This one addresses activity recognition problems, but also, just like the previous talks, it accounts for the lack of annotations that are hard to obtain for the active and assisted living context. So our speaker is Yue-Hei Ng. He's a PhD student at the University of Maryland, and he works with Professor Larry Davis. And his research is mostly on action recognition from videos. Thank you.
Thank you for the introduction, and also thank the organizer for inviting me to be here to give the talk. So this is a joint work with Zhongheng Choi, Jan Neumann, and Larry Davis. So we all know that CNN is very successful thanks to the power of end-to-end representation learning that is able to learn representation from raw pixels and then more progressively higher level features. And then more importantly, CNN also learns generic features that is able to transfer to other many different tasks that works really well. However, there is still limited success for end-to-end video representation learning because there is an extra temporal dimension that we are still unclear what is the best way to model them. So previous work on two-stream networks for action recognition is very successful. They separate the model into two networks. One is the spatial stream, which is the single RGB frame with ImageNet pre-trained network, which is pretty standard. And the second one is the temporal stream. Interestingly, they take 10 optical flow frames as input, which encodes motion. And the temporal stream is shown to be gives great improvement over the RGB networks. A natural extension of the image-based CNN would be 3D convolution. Like C3D and I3D, they pre-trained on large labeled dataset. However, even with pre-training on large-scale labeled dataset, the performance for action recognition can still be improved by two-stream networks. So we can see that although 3D convolution seems to be able to learn the motion, but in fact, it does not really learn good motion representation from the action classification labels, even with large amount of data. So we can see that CNN gives great performance with optical flow input, but is also slow to compute, and is a handcrafted input, so it does not take advantage to the end-to-end optimization. It is unclear whether this handcrafted feature is best for action recognition, or there could be anything better than that. Second, CNN is not effective in learning motion representation from raw pixels. We can see that from that optical flow improves the RGB performance, even with large amount of data. So one hypothesis is that action classification may be a bad supervision for learning the video representation for action recognition, because it is not able to learn everything it wants from raw pixels. Finally, another drawback of two-stream networks is that they cannot model the interaction between the appearance and motion. Like the RGB frame could recognize there is a dog, and the temporal stream could recognize something is moving, but it wouldn't know exactly the dog is moving, this kind of concept. Another line of interesting work is self-supervised representation learning, because labels are expensive to collect, especially for video, and also for domain-specific action recognition that we cannot gather a lot of videos in most cases. So previous work suggests to use self-supervised learning in videos, because videos has a temporal structure that can be exploited to learn a better representation that can be transferred to other tasks. So most of them do this by designing a surrogate task to learn visual representations. For example, previous work tries to leverage the order of the different frames and then ask the network to predict the order of the frames so that the network should learn the good semantic representation to differentiate the order of the videos, and then transfer them for action recognition. So the goal of this work is to learn motion representation for video action recognition. We want to do it without relying on handcrafted features as input, like optical flow, but we want to do it directly from raw pixels, RGB pixels. And we want to do it without pre-training on large-scale labeled dataset, because the datasets are usually biased and also hard to collect. We want to use the unlabeled data to learn a motion representation. In this work, we leverage the optical flow for learning representation, but not as an input. So this work is motivated by FlowNet, which shows that CNN can effectively learn optical flow by supervised learning, and it gives competitive performance among real-time methods. This is interesting because we can see that the 3D convolution doesn't learn motion really well. But the FlowNet successfully learned it. So we can see that it's not that the CNN architecture cannot learn optical flow, which is some people previously hypothesized. It is just that the CNN is not learning the optical flow, not learning the motion from the action labels. So our approach is motivated by FlowNet, which computes the optical flow from CNN. So the FlowNet learns the motion from raw pixels, which is what we want. We also based our work on ResNet because ResNet is fully convolutional and is especially suitable for pixel-wise prediction. We use optical flow estimation as a surrogate task for self-supervised learning. Oh, by the way, if you have any question, feel free to interrupt me. So to compute the optical flow from videos, we extend the ResNet to 3D ResNet for multiple frame inputs by replacing 2D convolutions with 3D convolutions. Also inspired by FlowNet, UNet, and also voxel-to-voxel networks, we use an encoder-decoder architecture where we take n input frames, we use 16 frames here, and output n-1 optical flow frames between them. In addition, we also ask the network to output the last final optical flow frame, which is the future optical flow. We do this because the first one is the practical reason that it is easier to implement the network with the same input and output resolution. And also, by extrapolating the future optical flow, it requires semantic understanding in the videos rather than simply matching the features between the frames. So that if it learns better semantic features, then it possibly better action recognition. A most intuitive way and simple way to transfer the learned optical flow motion in our FlowNet for action recognition is to simply fine-tuning the FlowNet for action recognition. So in the self-supervised learning context, it is basically using optical flow estimation as a surrogate task for representation learning. So we first trained a FlowNet, multiple frame FlowNet, and then remove the decoder and then train it for the action classification. However, such approach has a drawback, is that when the network fine-tuned for a new task, especially a very different one, like action recognition compared to optical flow, sometimes it will forget what it learned previously and overfit to the new task, action recognition. This is called catastrophic forgetting. To combat with this catastrophic forgetting, we proposed the ActionFlowNet. It is pretty simple. It is based on 18 layers of 3D ResNet. The main idea is to do multitask learning to jointly learn optical flow and action recognition. The idea is to use optical flow to help action recognition because when the network can learn optical flow, it should encode some motion information inside the network. And then when it also needs to learn action recognition, it can use the learned optical flow information and then to improve the action recognition. Some previous work on multitask learning suggests that it is possible that with multitask learning, the performance may hurt because two goals may be conflicting. But here, it is not the case empirically, and the reason is that Firstly, optical flow has shown to be very effective for action recognition. And then secondly, see in the network there is some skip connection from the encoder to decoder, so that in the higher layer in the decoder, it can kind of focus on the more abstract concepts, like for action recognition, instead of memorizing everything for every video details for output the optical flow. During inference, only the classification branch is needed for action recognition because, yeah, and then we can remove the optical flow decoder so that it can eventually have the same inference speed as a single task, single stream CNN. To quickly experiment different architectures and also do more ablation studies, we also trained a few two-frames based model. The first one would be the two-frame version of ActionFlowNet. And the second one would be a stacked model. This is basically stacking a classifier on top of a FlowNet. This is kind of similar to a temporal stream, but by replacing a optical flow input, we use a FlowNet and then use the FlowNet output for the classification. So for our experiment, we mainly trained our network on UCF101 datasets, which is all the numbers show will be on UCF101 dataset in this slides. And more importantly, we do not pre-train our network on large-scale dataset like ImageNet, Sports 1 million, or Kinetics dataset. And for training for the optical flow estimation, because action recognition dataset like UCF101 do not have ground truth optical flow. So to train it, we compute epic flow, which is a very popular state-of-the-art optical flow algorithm. And then we compute the epic flow on UCF101 as a pseudo ground truth. And then we train the network to output to match the epic flow output. So here, the color doesn't look great, but here is the example for the epic flow. It looks pretty decent and preserve the object boundary especially. So to compare our model, we first compare our two frames network. So our models, like by fine-tuning the FlowNet or the stacked model or the ActionFlowNet, all of them outperforms the baseline random initialization significantly by a large margin. And we can see that the ActionFlowNet two-frame version outperforms the FlowNet fine-tune, which shows that the multitask learning actually helps for learning motion representation. However, they are still inferior to ImageNet pre-trained network slightly, because ImageNet pre-trained network is very good at learning good appearance models. And then we look into the multi-frame model. So we can see the multi-frame model, ActionFlowNet, outperforms ImageNet pre-trained network. It performs very well, even without large amount of training data. So recall that ImageNet pre-trained model used like 1 million labeled images for training, and then our ActionFlowNet only used like 10,000 video labels for training. And then interestingly, when compared with other video-related models, ActionFlowNet outperforms the very popular C3D model, which was trained on Sports 1 million with 1 million labeled videos. And it is just not as good as the recently released kinetic dataset pre-trained i3D model. But still, we can see, even with such small amount of data, the ActionFlowNet can learn motion representation pretty well and is competitive to many of the existing state-of-the-art models. When we compare to previous work that just learn from raw pixels without pre-training on large-scale dataset, which what they do is mostly designing different surrogate tasks for self-supervised learning in videos. Basically, all they get is around from 50% to 60%. And our two frames version already improves them by a large margin. And then when we look at the ActionFlowNet without multitask or with multitask, we beat them by a very large margin, more than 23% improvement compared to previous work. To understand what is learned in the ActionFlowNet, we visualize the important regions saliency map for doing the classification. So here we can see some input images, which correspond to the original video, and then the optical flow output from our ActionFlowNet. We can already see that the optical flow looks pretty decent. And then here is the saliency map of the ImageNet model, which is trained on single frame and then model the appearance only. We can see that the ImageNet model focuses more on the appearance, the context. Like if you see a beautiful face, it's probably like applying makeup action. And if you see the writing on the board, it is probably the writing action. And then when we look at the saliency map of ActionFlowNet, our ActionFlowNet focus more on the action, the motion itself, instead of the other appearance context. And also, when we look at the writing example, we can see that our ActionFlowNet also focus on the writing action itself, and also it can look into the writings on the board, so that it can model the appearance and the motion in the same network. This is not possible with like optical flow input in two-stream networks. Here is some example of our optical flow estimation and prediction output, although this is not really like the main focus to get the best flow of our work. We can see that it gives pretty decent optical flow results. And the red border one is the extrapolation of the last future optical flow frames. You can see it's not really exactly just copying the last optical flow frame, but it's kind of learning some motion patterns inside. Finally, we want to understand how the quality of the optical flow estimation affects action recognition. To do this, we train a FlowNet, two-frame version of the FlowNet on the flying chairs dataset, which is a synthetic dataset, so we have the ground truth optical flow. And then we evaluate the different FlowNets on the Intel optical flow benchmark. And then the FlowNet trained on flying chairs dataset, not surprisingly, is more accurate than the FlowNet trained on UCF101 dataset because it has more accurate ground truth labels. But they are all not as good as the state-of-the-art flow algorithm like EPIC-Flow, which is also not surprising because EPIC-Flow is kind of slow and do a lot of optimization work for a pair of images. So after getting different flow, we train a stacked model, which is a classifier on top of the optical flow output with different optical flow based. And then here is the action recognition results on UCF101. So we can see that the better optical flow doesn't always translate to better action recognition. Look at the flying chairs FlowNet. It has better optical flow output compared to the UCF101. But the action recognition performance is really poor, like 51% on UCF101 is really poor. So why is that? So we believe it is because of the optical flow distribution mismatch in the datasets. Like flying chairs is a synthetic dataset consists of large motion. And then the endpoint error metric, which is what is evaluated on and trained on, also biased towards the large motion. So the flying chairs dataset, the FlowNet performs bad when the motion is small. Here, this is the output of the flying chair dataset, FlowNet, and this is the output on the UCF101 FlowNet. Notice that the motion here is small, like on average, only like 1 pixel movement. So this is in contrast to previous work that, like traditional optical flow algorithm, that they are good at modeling the small motion, but failed on large motion. So seeing this, we can see that the endpoint error on optical flow benchmark may not reflect the action recognition performance, but there could be many other factors that affect the optical flow performance. I mean the action recognition performance, like the smoothness of the object and the preservation of the object shape could be more important for action recognition using optical flow. So to conclude, we proposed ActionFlowNet to learn motion representation for action recognition. It jointly learns action recognition and optical flow from raw pixels to improve the action recognition. And it gives competitive performance to networks pre-trained on large-scale datasets. And we also do some analysis on quality of the learned optical flow for action recognition. And we see that better optical flow does not always give better action recognition. So more research could be done in understanding like what properties of the optical flow is good for action recognition indeed. And that's conclude my talk. Thank you.
Actions that have to be recognized, and this means that they will have to be segmented. Or does it just take into account individual videos where there is a single action and the question is just to classify the action?
So in this work, we only experimented on like a whole video classification into one single action label. But I believe this can be extended for like multi-label, like doing the convolutions on time dimension and like a sliding window for that.
Okay. Do you believe this could be done in real time, or I mean, how do you imagine this being?
I think this could be done in real time because all it does is just do the forward pass of the 3D convolution networks.
I have a question. ACL, I saw you use three-dimensional motion mapping, 3D WACV18 to design the network. And so for the decoder part, is it symmetric to the encoder?
It's not quite symmetric. So most of the layers are in the encoder, and the decoder is maybe like 5 or 6 layers only to reduce the memory usage.
The input, what is I think you use a clip sliding window. What is the window length?
We just take 16 frames input.
16?
Yeah, but like also as many other works suggested that if you extend the network to incorporate more input frames, the performance should further goes up.
And what is the resolution of the image?
224 by 224.
How many GPUs do you use
This I used 4 GPUs, and then it takes like 4 days for the ActionFlowNet. It was like using K80, so current GPU could be faster. And also I'm not like and my implementation is not optimized. So when I train it, the I/O is the bottleneck, so it can be further optimized.
I think the GPU memory also has a lot of memory.
Yeah, but
do you have some idea, or do you have some operation to reduce the GPU memory use?
I don't have any specific idea, but there are many general techniques to reduce the memory out there. Yeah.
Thank you.
It's just the fact that two-stream is so popular nowadays. Would it be possible that this type of method equipped with two-stream, the performance may be even more boosted?
I don't know, but I think the performance will not be the boost would not be as good as like the two-stream is shown because it's already learning the optical flow network. But what I'm interested is maybe when you train it with large amount of like appearance classification data, like with RGB, like kinetic dataset or other dataset, then when it has enough data for modeling the appearance as well, then the performance could further go up. But multitask learning is still like a difficult task when two objectives are very different, and yeah, the learning is sometimes fail when the task is not tuned properly.
Another question. We have paper has less parameters than 3D REST-API
Mhm.
get better performance.
Yeah, I believe there is a lot of work that can be done to improve the architecture. Like RESTnet is there's many improvement on RESTnet, like dual path network or REST-NXT or Inception or etc.
If you are interested, you can find out paper in this proceedings.
Sure. Yeah. Also, like what I'm interested, another interesting thing is that we can see the optical flow prediction network, like the newer version of FlowNet 2.0, is the architecture is quite different from a traditional recognition network. So another interesting future direction would be how to combine the best of both kind of architecture to further improve the action recognition performance.